Hello and welcome to the new Technique session 3.25 Quantum Computing with IBM. I am Mohit Gadvi, IEEE CS Senior Core Member, and today we are going to understand and go into the fundamental concepts of how quantum computers work. Well, we all know what today the importance that has quantum computer carried throughout these years. It is one of the cutting edge emerging technologies in the foreign as well as the Western countries, as well as if we consider in India. We have several companies in India as well as abroad who are working today behind spending millions and billions of dollars on behind the research to collab and to work collectively and get the good results from the quantum computers. And so today I have taken one such company who has made one of the best quantum computers so far till now, who has evolved along with the IT department. It has also hold on a position in the quantum computer research, and that is IBM. It's an American IT company, and today we are going to discuss on that. So that's the story behind quantum computing with IBM. And next we move on to the one of the most prominent quantum computers so far in the market industry. And this is the on the left, the CEO Krishnamurthy sir, of the CEO of the IBM company, and the front, which you can see the golden, very shining photo, that is the quantum computer. And this the name of the quantum computer what IBM has given is the IBM System 1. So that's the name, IBM System 1. And we'll discuss just carefully, see the picture, and we'll then discuss what are the specs and benefits of this quantum computer and the research behind this. And on the right corner, which you can see is just behind this, is the quantum one of the best computers, quantum computers of IBM, made by the IBM, with having 433 qubits. uh, and this name is given is Osprey. So you have the layers. The beneath layer, the undermost layer is the chips, quantum chips that are integrated to each other, and on the top of that layer you have the wirings, and similarly another quantum chip level, because since it is a 433 qubit, so you have the chips have been stacked onto a layer uh, in between the layer of the wiring, right? So this is a record breaking qubits in terms of quantum processor so far ever built by the IBM, or if you take any of the IT companies, right? So we'll move to the next, and this is actually the big picture of quantum computers as very zoom and enlarged clear image of the quantum computers. Now I'll share you some interesting facts about this quantum computer and how it works. So basically, to the temperature to keep these qubits, which I'll discuss in the later part of this section, what qubits are, to the temperature to keep these qubits is almost 15 millikelvin, the coldest temperature so far in the universe. It's even colder than the outer space, right? So you have refrigerator technologies. We have machines from uh, Finland. They give the refrigerator technology, and you store this quantum computer inside this to work on the qubits. And as I already mentioned, it's the name of the quantum computer is IBM System 1. The part that you are watching right now, that makes keep going this quantum computer at this insane temperature, and all these cables that you're seeing on the side that are carrying signals, and they carry the signals down through the fridge into the processor that is beneath the wiring layer, right beneath this. you have the processor chip, and they perform the quantum stuff, basically what we call the calculations, and they send the same signals to the control electronics which are at the room temperature behind this quantum computer to understand the calculations for humans, right? So this is how it works actually. The main core fundamental behind the working of this quantum computer. You take it any computer, if you have even the Chandelier, which is the name given by the Google quantum computer, that they also work on the same basically this principle. Now, we'll move to the next slide, right? And we'll see what basically so far we have evolved through these technologies. So currently we are at the stage of quantum computer edge, but we do not have to forget what classical bits give has taken the importance so far in this industry. So classical bits are basically two things, that is 0 and 1. Now, we need to understand the fact that even today we have not been able to achieve building a parallel computer system in terms of our daily usage, right? So what we see as electronic gadgets near us have a speed such that we feel that it's doing a parallel task simultaneously, but it's actually not. So, due to its high speed, we fail to recognize it is doing serial computing, right? And we call it zeros and ones as the binary bits, which are very famous in the computer language. We call it even assembly language programming and ALP, that's we call. And basically, whatever we see, the images, the sound, the calculations, all are done at a very low assembly language programming only on the two things, zeros and ones. It's a combination of these two. But in qubits, you have zeros and ones, and as well the stage between the zeros and ones. I mean, the phase is between the zeros and ones. That's we going to see in the next slide. But remember, in classical computers, there are only two things, zeros and ones. Zero is called the ground state, and one is called the excited state, right? And this is how we come to the next main concept, that is the core concept behind how quantum computers work. And these quantum computers work on quantum bits, which are basically known as qubits. Qubits are basically, if I give it in a very simple definition, it is an addition of the constructive and the destructive waves while calculating the large amount of data. So the quantum bits or the qubits are the basic unit of information that we store in the quantum computers, which are the counterpart what we do in as such in the classical computers, right? The quantum theory, which allows the quantum physics to understand the branch. This is what the fundamental branch which describes the physical phenomena at a very atomic or subatomic level. We have we have at very subatomic levels, we have electrons, photons, and neutrons, and the molecular scale objects are sometimes called reality, right? We shall discuss more about these qubits and how quantum computers work. So first we'll see some what is the difference, direct comparison between the classical bits and the quantum bits. In classical bits, we store the large amount of data in the purpose of multi-purpose computers that we devise that we see today. Whereas quantum bits are used by high-speed quantum mechanics based computers which follow the quantum mechanics rules. We store the information in bits in classical computers, and we store the information in qubits in the classical in the quantum computers. We have zeros and ones as classical bits. We have zeros and ones and the phases between 0 and 1 in qubits. Calculations are deterministic, that means you can get the same output with repeating the same input. And here in qubits or the quantum computers, the calculations are based on the probability. meaning there can be multiple outputs for the same input. In classical computers, the data processing is carried out by the logic. That is, you have the logic gates, AND gate, OR gate, and in the sequential order, right? So you perform AND gate, then OR gate, then XOR gate, and similarly in the sequential order. But in quantum computers, the data processing is based on the quantum logic at a very parallel instance. So if you want to perform 2 plus 4 plus 6 plus 8 plus 10, you will see that a classical computer does the same work after adding 2 to the adding 4 to the adding 6 to adding 8 to adding 8 10. But in parallel system, it will divide the calculation through parallel processes, and then you get those results at adding at last, right? So this is how the very basic example what we used to learn in our lower classes, and this is how basically a quantum computer works. That is mainly on the parallel instances. So next we have a pictorial representation and a comparison between how bits work and the qubits work. So on the left of the screen you have uh, all these photos, the data, all the data information that is stored in the computer is totally based on the bits, that is zeros and ones. So you perform some calculations on assembly language programming and you get the result. That's the main principle of classical computers. But in qubits, it's more of, if you see carefully, there are waves, right? If you put a stone into a pond, you get a wave created, right? That is how it watches, the quantum computers watches how all these waves interact and then find the most likely answer. This is how the quantum computers work behind, right? So this is how the qubits interact and we find the most likely answer. Now, very good question. How these quantum computers work actually? So you have three main building blocks of computer. You have qubits that we have already understood. You have superposition and you have entanglement. Both these core concepts, I'll make it in a very simple language, very easy to understand in the following slides. But we shall discuss what's the description of how quantum computers work, right? So basically it works on the principle of quantum physics. Like we have in classical computers, binary bits, we have qubits and quantum computers, and how they work is basically scientists or the researchers manipulates these qubits to work on the quantum computers. So in the very first slide I mentioned why we need a very low cold temperature, because to work on these qubits, that is electrons or the photons, we need to have a very low temperature to maintain them at the very I can say ground state, and then performing some actions they may get into excited state or the state in between the ground state and the excited state. That's what I already mentioned. So this is how qubits work. So qubits is not really only ground state and high excited state, but it also works on the between the phases of the ground state and the excited state. And the quantum computers promise to do the computation more powerfully than the classical computers, but it's actually a very misconception that I'll clear at the end of this slide. Ability of a quantum computer to be in some state that have no equivalence in the classical computer, such as a superposition of the values and the entanglement between some particles of the quantum system. This is also I'm going to make you understand in a very next slide. But so far, what I wanted to make the conception is that it's a common misconception that quantum computers try all the options. It's not actually like that. Quantum computers calculate the things very differently. So quantum computers are not faster at everything than classical computers, but the things that quantum computers are good at is finding the structure in tons of data. So basically, you are altering the possibilities while you are running an algorithm. So you have uh, one of the most famous algorithm, Peter's algorithm, that I shall discuss in the very next slides after entanglement. And we'll now move to the basic building blocks of the quantum computer, that is superposition and the entanglement. But before that, yeah, very important, why quantum computers are needed. So you have a very famous problem statement, that is salesman's problem statement, wherein you travel the salesman is traveling through across many of the cities, and we shall find the shortest possible route. Now, basically, while we code, we find through the brute force algorithm or a dynamic algorithm. But in quantum computers, we shall discuss the direct comparison between how fast a quantum computer can give and how fast a probably a classical computer can give. So this is the pictorial representation of the traveling salesman problem. If we had 14 cities, there would be 10 power 11 routes, which will take for a classical computer to perform in the 10 seconds. If we had 22 cities, it would almost take 771 years for a Intel any of the best processors so far. So we are assuming this classical computer speed at a 4.4 gigahertz. That is the Intel i7, so far one of the current Intel processor, which performs 10 power 10 operations per second. And if we had 28 cities to travel, we cannot find the time taken for making a shortest possible route, because it may be even much more complex. It can be even older than the universe, right? So why am I discussing this is because if you take a classical computer in terms of very basic calculations, we have already the phones and gadgets and calculators that are doing pretty well instead of quantum computers. We don't need that. But when you are going for higher research on molecules, biomedical sciences, then you need a quantum computer to suppose if you want a better, uh, I can say, a better patent or a formula for a medicine or a drug, you go for quantum computers because that's how their probabilities are calculated. As I already mentioned, you find the interaction between those waves and find the most likely answer. But here, while traveling salesman problem is included, is considered, we don't need quantum computers. Now, one of the basic blocks what I was going to tell you is why those quantum computers are different and what is different about them. So we are going to explain three concepts: quantum superposition, quantum entanglement, and quantum teleportation. Everyone know that we have quantum numbers denoted by N, L, Ms, and Ml. But today I'm going to only talk about electron spin quantum number, that is Ms. So basically, each electron has either a positive spin that is we call as spin up, and a negative spin that we call it as down spin, as shown in the image. But it doesn't mean that it spins in either one of these two, but in reality, in spite of the fact that electron has, I can say, angular momentum, it has also the speed. But then still why it doesn't spin? It doesn't spin because it's in the superposition state, right? So in bits, you have zeros and ones, as I already mentioned. So either you have a spin up or down spin. But in qubits, you can also find 0 and 1, and also in between all the phases or all the angles between the zeros and ones. So superposition, that's we are going to understand how it works, and it is one of the primary key or core concept behind quantum computer. But before that, before understanding quantum superposition, we need to understand the Stern-Gerlach experiment that I'm going to show a small video. We'll also discuss elaborately on the conclusion of the video, right? So, so I'm going to show one animation about the how quantum the spin works. It's a quantum magnet. I'll show the video. So you have two magnets, North Pole and the South Pole. You have magnets that you throw in between those, and the magnets form a shape behind by sticking on a behind screen. Now, what we did actually is in this Stern-Gerlach experiment, we made two bar magnets, North Pole and the South Pole, but we made one pole more stronger than the other one by intentionally not providing uniform magnetic field, because if we provide uniform magnetic field, then it will not allow to spin, unlike in the uniform, right? So point to be noted here is one of the pole is more stronger than the other, and in between those poles you throw a magnet, uh, and the one uh, side of the magnet which would be attracting to each other would likely cause to form a formation behind the screen in such a way, either in the north pole and the south pole, right? And now what's next? Now these are electrons. Look at the formation that they are sticking behind on the screen. So what you observed is, so if you simply look at the electron, you cannot judge without this experiment whether it has a up or a down orientation of spin. Hence, before determining what orientation it has, it is said to be in superposition. And that's how this Stern-Gerlach experiment uh, trails about what the superposition actually looks like in a quantum computer based on an experiment of an electron. So if obviously an electron has either a spin up rotation or spin down orientation. So whichever pole it will attract more, right? Because again we have not given uniform magnetic field between those magnet poles, so based on the attraction law, it will stick behind the screen in such a way either it will show a north pole upside and either a south pole on the upside. So this is how formation it takes place. It does not stick in a one straight line, but all the attractive poles will attract each other and uh, attach in the same line, and similarly for the vice versa. So what we actually wanted to conclude is, so as soon as we measure one of the orientation, we can determine the other. That is called quantum entanglement. But in Stern-Gerlach experiment, more of it was explained on basis of uh, providing uniform, not non-uniform magnetic field. The behavior of these electrons and the magnets are totally different. So that's what we need to conclude, that it's not the electrons will have the same behavior as we have the classical Newtonian laws that work for the magnets. Here in Stern-Gerlach experiment, that was the key concept, that electrons work on non-classical Newtonian laws, that is called the quantum laws, right? So this is what we needed to conclude of this Stern-Gerlach experiment, right? So this is what actually I wanted to show you, how the quantum superposition principle works. So you have, if you carefully observe, we have three coordinates: x coordinate, y coordinate, and z coordinate. A particle moves in 3D coordinates, having independent each x, y, and z coordinates. Similarly, a qubit does. There are probabilities. Uh, if we say that the probabilities were equal, the vector could be represented as 45-degree, because either it can be 0 or 1. If the probability of 1 were twice that of 0, the vector could be represented as 30 degrees from the vertical. And if the vector represents the superposition of the probability of zeros and 1 simultaneously, in this way we call the state of the vector, that is classical bits are collapsed and qubit state vector is achieved. So that's I'm going to discuss. There's another concept called collapsing of the wave function that I'm going to discuss in the next upcoming, just next slide. Superposition is basically this: if I take in a very simple language, you toss the coin, and if it's in the air, it's obviously spinning in the air. You cannot predict whether it will fall down as a head or a tail, right? Similarly, you cannot predict it will fall as a zero or in a one state, that is the ground state or the excited state, until it stops. But if we consider all the probabilities while it's in the air, revolving or spinning up, there are chances of either 0 and 1, or also the phase between 0 and 1. So now I'll move to the next slide. Now we'll understand what quantum entanglement, which is one of the basics, important principle behind how quantum computers work. But before understanding that, I'll explain with you a very small example, easy example. So if you have samosa and pakoda in two boxes, without opening box, you cannot define what would be inside it. Once you open, and if you find samosa in one of the box, so on basis of that, you can predict that the other box would be having pakoda. This is how the quantum entanglement works similarly. For now, let's suppose that any particle which is in a superposition, which means that we don't know its actual spin, and at the time duration and its time duration from not knowing the spin to determining the spin is called collapsing of the wave. So collapsing of the wave simply means that determining the spin is called the collapsing of the wave. Now, to understand more, we have quantum entanglement associated with one of the famous scientists, Schrödinger. So Schrödinger had a cat experiment that also I'll share with you in the very next this slide. Uh, what is quantum entanglement basically? It has the ability of a quantum system to establish a relation between the two states in a superposition. So if you have an electron pair that is in a superposition, quantum superposition, so quantum entanglement will establish a relation between these two electron pairs. And quantum entanglement is also one of the central principles behind the quantum physics. That is, it is too also highly misunderstood, and many famous scientists are unable to understand it. But in short, it's basically a establishment of a relation between these two quantum superposition particles. It can be either electrons as well. In short, this quantum entanglement means multiple particles are linked together in such a way that the measurement of one of the quantum particle or the state is determined by the possible quantum states of the other particles. When this happens, the state of the two particles is said to be entangled. So, forget about this if I tell you there's an electron pair that exist in this universe. Now I put these electron pairs one into another universe and second into a totally different another universe. Still, if I tell you that these two electron pairs or the particles are quantum entangled, so it means there is a distance relationship or a correlation between these two particles. So if I determine one of the electron having either spin up orientation or a down spin orientation, the opposite that is into the different universe will have the opposite orientation. If you say that the electron pair is having a spin up orientation, the another particle that's in the different universe will have a downspin orientation. So this is what quantum entanglement in a very easy language I can understand you, make you understand, is basically there's a definitely a relation or a correlation between these two particles, and that's why both these particles are called quantum entangled, right? And how what Albert Einstein believed about this? So he said, but before that, let me remind you, the point to be noted here is the atomic particles which we focus or study on, either electrons, uh, these atomic particles do not follow classical mechanics rules. They only follow the quantum mechanics rule, and things become out of logic. And that's why the famous mathematician or the scientist Albert Einstein said, spooky action at a distance. And why he said? There's a story behind this. So, these were the three main scientists who proved Albert Einstein wrong his model of relativity about the quantum electrons. And why, I'll make you understand why Albert Einstein called it spooky action. So, so far in universe we know that nothing is faster than the speed of light. That's right, correct? But it was proved at the time of Albert Einstein that if the two particles are quantum entangled, they travel faster than the speed of light, right? No matter they are however distance apart from each other, but they travel or communicate with each other, that the correlation or the relation established between them, that medium where the information is interacting with each other is running faster than the speed of light. So that's why Albert Einstein did not believe, because according to his theory, nothing can travel faster than the speed of light. But actually, it was proved that it was faster than the speed of the light. That's why he's called spooky action at a distance. And these three scientists were the awarded Nobel Prize in 2022. Sir Alan Aspect, Sir John F. Closure, and Sir Anton Zeilinger. These were the scientists who proved, one scientist proved that the theory behind the model of relativity was wrong. Another proved the drawbacks of this theory, and similarly, the third scientist. And that's why they were awarded Nobel Prize in physics for working on quantum physics in 2022. And this is how quantum teleportation, another key concept, was established. So basically, in short, teleportation means a communication. Quantum communication. What is quantum communication? That I already mentioned. So if you have a quantum entanglement, two particles or two electrons, the information interacting with each other of these two particles, that is called the quantum teleportation. So you have it's a technique to transfer the information from one quantum level to the another, from one particle to the another. Similarly, it's a distinguishing feature that it can transmit the information present in the quantum superposition, useful for the quantum communication that I already mentioned. So that's why these information that is traveling much faster than the speed of light. That's why scientist Albert Einstein believed that this is called a spooky action, and this is why I mentioned that quantum electrons do not follow Newtonian laws, the classical Newtonian laws. They follow quantum mechanics laws, and that's why they are different and things become out of logic, right? Now we'll move into the applications. There are wide variety of applications, and the scientists and the researchers are working behind this. And to be very honest, till now we have achieved 433 qubit fastest processor in the current industry of quantum computers. But scientists are predicting, researchers are doing research that we can also have million qubits processor chip in the upcoming years. And there are so many lots of MNC companies giving funds, providing funds for the research of these qubits. And that's why I called, because to maintain to work on these qubits we need a very low temperature. That was the this is what the main problem is actually about. But before going into the advantages and disadvantages, we look into the applications. So we have encryption technology. This is a very important and interesting application of encryption technology, which I'll make you understand in a very easy language. We have ultra secure and super dense communications, molecular simultations. We have cryptography. We have factorization. We have true randomness, searching, and simulating. Now, why I told encryption as important and the interesting topic, because many of the federal governments, basically the US government and all the different countries governments have their encrypted data. If I talk about India, we have Aadhaar card, we have UADI working behind running all the Aadhaar card data, and they are highly encrypted. So to to collapse this encryption, we need millions of qubits to break this encryption. And if you are interested in developing the battery technology or creating new materials that you have long chain of molecules, for that you need quantum computers. Now you need either new medicines, new molecules. So mainly the quantum computer can do way better efficient, and breaking of this encryption may take millions of qubits to do. But scientists and the researchers are working behind it. But so far we have uh, not focused on the area to decrypt these encryptions, but rather to focus on the algorithms, running of the algorithms to work on a better stage and get the outputs more efficiently than the classical computers, right? And that's why I mentioned in between my explanation that quantum computers are used to get the structure in tons of data, right? So, uh, I'm going to explain, since we saw the applications, now I'm going to explain you what are the advantages of quantum computer. We shall discuss few points and then I'll explain you what I was actually going to explain, as I already mentioned why encryption is more important and interesting topic. So firstly, its more advantages are it can process massive amount of complex data. it has the ability to solve scientific and commercial problems that we already discussed, that is um, traveling salesman problem. So you saw that the number of routes were 10 to the power 11, 10 to the power 22, and so on. So that quantum computers are used and the output is much more efficient. So the reason behind this is obviously it does parallel processing, parallel computing, and that is why the result obtained is very accurate. I cannot say accurate, but yes, very fast, right? Compared to the classical computers. Third thing is processing the data at a very much faster speed. Fourth, capability to convey more accurate answer. More can be computed in a very less time, and that is why they are used for protecting the web page or the encrypted mails, and even processing other types of data. Now, the reason behind why the federal governments are more worried about encryption of data, and why they believe that quantum computers can, break the encryption code of these data, but it's actually not. Now my question to you and everyone is, why everybody is so obsessed with talking of quantum computers and encryption? The answer is, so the first major algorithm was Peter's algorithm, which was named after Peter Shores. He was a nice guy, he was a good scientist, and he invented this algorithm which basically find the factors and the prime factors for a very really large number. And why? Why does anyone care about this? The question is right. Why does anyone care about this? Because that's the basic of RSA encryption, which is one of the type of encryption, and which is basically how all the transactions on the internet are conducted, and the entire reason that all our encryption schemes today work that the that way is because it's basically impossible to crack this with a brute force classical algorithm. Now, if I take quantum computers and if I take classical computers, so with classical computers, you cannot break these encryption codes with a brute force, but in some of them, scientists believe that they can break encryption codes through millions of qubits of the federal government data, but it's actually not. So right now, the researchers and the scientists are not more into breaking these encrypted codes, but they are more likely to perform complex calculations which are not done by these classical computers, right? And that's why encryption is a concern issue for rest of the world. And now we come across the last part of our session, that is the disadvantages and the problems. It is hard to control the quantum particles because you need a very low insane temperature. There is a lot of heat produced behind these refrigerator technologies. It's expensive. It is difficult to build, so you have more monitors, lots of monitors to understand the calculations at a room temperature, as I already mentioned, and you need so many wirings, and it's really very difficult to build that. You need quantum chips that can be integrated. So remember, just think about 433 quantum chips to make that processor. It's really very difficult to integrate these circuits, not suitable for word processing and image. That's obviously true. It has a problem which is making much more noise, and we need a free and cool environment. So this is the problem, and climate is also one of the global concerning issue. And the last point is it has a complex hardware and schemes like superconductors. If you see in a bits or classical bit chip, that is processors that we have right now, they are easy hardware, means it is easy to implicate and stick the integrated chips or the modulars into a one processor. But whereas in quantum chips, it's really very hard. The complex structures are not that easy as compared to the ones that we have processors right now. So yeah, this was my explanation about what actually quantum computers work and how IBM is evolving these technologies along with the competition. And thank you for having patience to listen to my explanation and the presentation. Thank you very much.